Hey there, everyone. Welcome to another PS Platypus recording. Today, we're going to be looking at fluid osmolarity and water balance, which forms one of the CR lectures in your series for kidney physiology. So without any further ado, let's get started. The first thing that we're going to be looking at is a prerequisite topic for any sort of discussions on fluid, which is the distribution of water throughout your body compartments. Now, I know that you've had extensive lectures on this in first year, so when you looked at your basic physiology of water, but I'm going to be trying to focus on some of the key relevant things when it comes to kidney physiology. So some basic details to be familiar with. The average adult human body contains about 60% water by volume, so that constitutes 42 liters. That number tends to decrease with age, and so you get progressive dehydration as you get older. And generally speaking, the average female human body will contain less water than the average male human body. And the reason why is because the female human body tends to contain more fat. Fat stores less water than muscle. In healthy people, the total body water hardly changes, and the reason why we'll go over the reasons why that's the case in the next couple of slides via some mechanisms that we'll become familiar with. But you tend to have a lot of inputs, a lot of outputs. We have to make sure that this number is fairly constant so that we're able to go about our daily functions. When we try and separate this out, we can think about it as intracellular or extracellular, within the cell or outside the cell. Within the cell, you have more fluid. So that's about 2/3 of the volume, which is 28 liters. Extracellular is the remaining 1/3 or 14 liters. And you can separate this in terms of location. So plasma, so for example, within blood vessels, you've got the interstitium around the cells, and then you've got lymph, which acts as a way to communicate between the interstitial fluid and the plasma. You've also got an extra definition called transcellular space. And this is not really that important to know, but I think it's mentioned in your lectures. It is essentially a space that's separated out from your general ECF by an epithelial layer. So the easiest way to remember this is to think about cerebrospinal fluid, or CSF, which circulates around your brain and spinal cord. If you think about the brain, that's separated from the rest of the ECF by the blood-brain barrier. And there's a lot of functions of that, which we're not going to go over here, but it's just useful to know that this word also exists. Now, when it comes to osmolarity, again, a very important definition that you will recall from first year. The definition is essentially the number of osmoles per liter of solution. And the reason why we look at it is because it determines the distribution of water around your body. Generally speaking, all of the body fluids around all of the body fluid compartments around your body will have the same osmotic pressure at around 280 milliosmoles per liter. In other words, everything exists in equilibrium, which we know kind of makes sense. Therefore, the osmolarity we would expect is equal between plasma, ICF, ECF, whatever compartment you can think of, with very, very few exceptions. The ICF and ECF, again, as we know, are also separated by a semi-permeable membrane. So they allow some things to go through, other things not so much. And this leads to a different constitution of ions across each of the spaces. So in the ICF, you tend to have more of these potassium ions and also anions that are mainly proteins. Whereas in the extracellular space, I like to think of this as the salty space because it tends to have a lot of sodium and chloride ions. Also, the plasma protein contains plasma proteins. And obviously, this list is not extensive. There are many, many different ions that exist. These are the main important ones when it comes to kidney physiology. Another thing to realize is, as I kind of mentioned, you have a lot of inputs and a lot of outputs. For example, you drink a lot of water, so that's an input. And you also get rid of water through urination, as well as through other mechanisms that you can see in the diagram on the left. The main thing to remember, though, is that your body will still try and maintain equilibrium to the best of its capacity. So, for example, on the right-hand side, you can see a diagram where it shows the ICF and the ECF represented as boxes. They are represented in terms of the volumes. So ICF is about 2/3, ECF is about 1/3 on the horizontal axis. If you look at the vertical axis, they're both the same osmolarity at about 280, 290. Now that purple box there, or the pink box there, illustrates what would happen if my volume of the ECF increased. For example, and it wouldn't increase by this much, but for example, let's say you drank a huge amount of water. So your ECF just increased drastically. Now, obviously, when you have an increase in volume, you'll have a decrease in osmolarity, which is why the box is now stretched out a little bit. But this is not going to just be like this, right? The ECF is not going to be stretched out and then the ICF will stay normal. The ICF will also somehow try and reach equilibrium. And the way it'll do that is that water from the ECF will go into the ICF to try and bring down that osmolarity as well, until eventually ICF and ECF are balanced out. And that equilibrium is super important for reasons that we will go over in the next couple of slides. And I believe this diagram that you're seeing here is something you'll be using time and time again in your lectures and workshops. So it's good to get familiar with this, and it's a really nice way to visualize how the different osmolarities can change. All right, now let's get to the physiology aspects. So how do we actually detect these changes in osmolarity, and how do we then launch a response? The main ways that we do this are through the paraventricular and supraoptic nuclei within the hypothalamus. They're the ones that respond to any changes in osmotic pressure. You'll go over this in more detail when you get to the pituitary gland later on in endocrine. But for now, just remember that the hypothalamus is where this is all happening. The hypothalamus, or the nuclei within the hypothalamus, extends their axons into the posterior pituitary gland, and those axons are lined with these things called Herring bodies. When the interstitial fluid around the osmoreceptors, which we'll go over in the next slide, becomes hypertonic, so in other words, it starts to get more ions and less water, then the receptors will start to shrink. So an easy way to think about this is everything becomes salty. Those osmoreceptors that are designed to detect osmotic changes, they'll start to wrinkle, as if you've just come out of a swimming pool, right? Your skin starts to wrinkle because of the salty water. When it starts to wrinkle and shrink, its firing rate will increase, and the Herring bodies, which we talked about previously, will be stimulated to release all of their stored ADH, or antidiuretic hormone, which we will go over in the next slide. So the easiest way to remember this is just to think whenever things become hypotonic, the osmoreceptors shrink, and then they will release their hormones. In this case is ADH. So what does ADH actually do? Well, the name suggests everything. So antidiuretic hormone. Diuretic means that it will cause you to pee more. So antidiuretic means it's going to stop you from peeing. In other words, retaining all that water when you're dehydrated. So another term for it is vasopressin. All it does is it binds to receptors within the distal tubules and collecting ducts of the kidneys, specifically within the nephron. And the way it does this by kind of like at a smaller scale is the phosphoproteins are made that bind aquaporins, so things that allow water through, into the membrane. These channels let water to escape the tubules and then return back into the plasma. So they're being diverted away from the urine and back into your blood. So if you imagine cases in which you would actually have hypotonicity, for example, dehydration, this would be very useful because now you get that water back and you bring your tonicity back to normal. Interestingly, this is just an important, not so important, it's an interesting fact to know. ADH shows a circadian pattern of secretion. So it will increase in the morning, decrease at night, which is why when you wake up in the morning, you feel like you need to go to the toilet. But while you're sleeping, hopefully you're not feeling like you need to go to the toilet. However, sometimes if it's not fully developed, either pathologically or if you're like really, really young children, in which this is still a maturing system, this decrease will not happen. So it's still trying to fine tune and learn how this stuff works. So it's not going to decrease, which means that you will feel like you need to pee at night, which is called nocturnal enuresis. So you're still producing a lot of volume of urine because your tubules are not able to resorb that back into the blood. So the way that you can solve this is via desmopressin nasal sprays. And as the name suggests, desmopressin is just an artificial version of the ADH hormone. So the response to dehydration, and this is just a way to summarize everything we talked about so far. Let's say you've got reduced water, which means your osmolarity in the ECF will increase. So it'll be higher than normal. The osmoreceptors, they'll start to shrink, and then their firing rate will increase, telling it's like a warning, right? Like your ECF osmolarity is way too high. We need to bring it down somehow. So as the firing rate increases, the posterior pituitary then releases all of its ADH stores. This increases the expression of aquaporins. Water gets resorbed back into the blood, away from the urine. And so your total body water is increased, which means your ECF osmolarity will decrease back to normal, hopefully. Okay. Now this is not only when you have dehydration. There are also other states in which you might have ECF osmolarity that is way too high, which you'll go over in your workshop. So I don't want to spoil that too much. But there are multiple reasons that are not to do with dehydration. This is just the easiest way to think about it in terms of physiological step-by-step process. So if you remember the 6 steps, you're fine. Now, how do the kidneys concentrate urine? And also, more importantly, why do we need to concentrate urine so much? So firstly, if we go through the different steps that the filtrate takes when it ends up out of the afferent arterioles that are in the glomerulus, ends up within the Bowman's capsule, goes through into your nephron, gets filtered through, and then ends up as urine. It goes through these multiple channels, which we know about from our anatomy learning. So firstly, in the proximal tubule, because it's filtered directly from the blood, it's going to be osmotic to the plasma that it was originally from, okay? Which means that the waters and the solutes are still going to be resorbed in an equal proportion to what they were originally, right? So that's fairly obvious. When you get down to the descending loop though, so as you go down the proximal tubule into the descending loop of Henle, they start to become hypotonic, the fluid. And the reason why is because these channels around the descending loop, they're more permeable to water and they're not permeable to salts, so Na and Cl, which is why water gets to leave and it becomes very, very hypertonic because now it's fully ionic. However, when it rounds the bend and gets into the ascending loop, suddenly all that water channels shut down. So the water is still going to be retained, but now all the ions get to leave. So in effect, what's happening is canceling out what was done before. So you start to get back your tonicity, and in fact, it gets very hypotonic when it gets up into the ascending loop. You're probably wondering, like, why would we do that? Why would, we're negating the process? What's the point? The reason why is because what this is supposed to do is something called a countercurrent mechanism, which I'll go over in the next slide. But essentially, it's trying to create, like within the loop of Henle, it's trying to create a very hypertonic region so that once we get later on in the tubules, we're actually able to resorb things passively. So when we look at the collecting ducts, so the water goes through distal convoluted tubule, blah, blah, blah. It goes down into the collecting ducts. Water is going to be able to leave from the collecting ducts without requiring energy, because what we've done with the collecting tubules is made the space extremely hypertonic. So now water just wants to come out, right, as passively as it can. Why would we do this? Well, let's say we are in a dehydrated state and we do want to retain as much water as we can. We need to have some way to fine tune our urine so that we're not getting rid of too much in our in our urine, right? We don't want to get too much water rid of through our urine. So the way we do that is via these hormones. So we talked about ADH. There's also aldosterone, which we'll go over in probably endocrine rather than here. But they allow us to either have our urine be very, very concentrated or not so concentrated. So the way that I like to think about this is everything that happens before the collecting duct is out of our control. So where this place, the loop of Henle, is going to be hypertonic no matter how hard we try not to. It's just always going to be like that. The thing that we can change, though, is what happens in the collecting duct based on the hormones that we release. So water is naturally just going to want to exit as much as possible out of the collecting duct because we've generated a hypertonic state somewhere else. But the vasopressin and the ADH and the aldosterone, that's going to be the thing that keeps things in check. It's going to say, okay, yeah, let's just let the water run free and go out so we can concentrate the urine. Or if we don't want to concentrate the urine, then let's not have as much ADH, let's not have as much aldosterone, and let's just let the water pass through as it normally does. Okay, so water just wants to go through. ADH and aldosterone is what's keeping all of that in check and figuring out, okay, do we need to concentrate it more or do we need to concentrate it less? Hopefully that makes sense. And if it doesn't, in the next slide, when we go over the countercurrent mechanisms, which is what I was saying in terms of when you go down the loop of Henle, it becomes more hypertonic. When you go back up, it becomes hypotonic. And what ends up happening is that in the middle, you get this very, very hypertonic medullary interstitium. And that's what is able to draw water passively out of the collecting ducts. Now, I remember the first time that I looked at this, it was very, very confusing. And the reason why is because if you look at a textbook, it's just going to show you a picture like this. Albeit it's not going to be in Russian, I think, like the one that I've put here. But suffice to say, it's going to be very, very difficult to actually figure out what this actually means. And the reason why is because it all needs to be actually, like this actual mechanism is quite dynamic. So you need to see multiple steps before it actually makes sense, which is why I've linked 2 videos here, which I use during my studies. And they really, really help to consolidate all this information. Now, one thing I will say is that this is not actually like super high yield. So this concept of a countercurrent mechanism, I doubt they'd ask you a specific question about it. But as long as you know what it means and you know that it's something to do with concentrating the medulla and to make it very hypertonic so that water can passively flow out of the collecting ducts to concentrate urine, that's more than enough. Also, another thing that kind of follows on from that very nicely is that if you have a longer loop, it makes sense that you're going to have slightly more concentrated medulla, which means you're going to be able to resorb more water out of the collecting ducts. And this is seen in animals like the desert rats, which, as the name suggests, they need to conserve as much water as possible. So sometimes even desert rats will have really crystalline urine because they've actually absorbed all the water back into their body, which is important for them because they live in the desert. So hopefully all that makes sense. I know that the countercurrent mechanism can be really confusing. So I'd recommend watch these 2 videos. If you still have any questions, watch your lecture again. And again, if you still have any questions, just reach out to me and I can try and help you with some extra resources that I might have used. But other than that, I hope you really enjoyed and I hope that you learned something out of this lecture. I'll see you in the next one. Best of luck for your studies. Peace out.